Okay, so as described on the last slide, efficiency, we'll just do it as EFF. There is no real, as far as I know, any particular shorthand for efficiency, but it is the amount of work put into a system and the amount of, you have to compare the amount of work that you get out of a system and the work that you put in, or the energy out versus energy in. So in this case, we have a machine that does 80 joules of work. So the useful work we get out of it is 80 joules worth. Again, remember, joules and newton meters are the same, so we can interchangeably use those units. You have to kick in 100 joules of energy. And therefore, when we do the division here, 80 divided by 100 gives you 0.8. And notice that the joules cancel. So this is actually a unitless quantity. Another way of saying 0.8 is also 80%. So this machine is 80% efficient. That's one way of saying it. Where's the missing 20 joules of energy? Because remember, we started with 100 joules of energy. We only got 80 joules of useful work out. So where did the other 20 joules go? Into another form of energy. They're not destroyed. That energy is not destroyed. It's impossible to destroy energy. It simply goes into a form that is less useful, perhaps heat or sound or something of the sort. Now in question 2, it says, okay, we've got a 80% efficient machine. How many joules of energy must be used to perform 120 joules of work? So notice that we have the efficiency already. We know its efficiency is 0.8. And we know that the energy out is 120 joules. So the question is, how much energy in, or how much work in? So energy in is what we would solve for. And you have to do a little bit of rearranging here, but I believe if you do the math, it winds up being, I think it's 144 joules of energy go in.